And as the first speaker, I would like to welcome Celal Senghor to the floor to give his presentation. Celal.
Thank you very much, Peter. Well, it's a great honor to have been invited to give one of the Union lectures here. I was saddled with the task of about talking about some aspect of the Earth, but lately I have been involved with 2 other planets. So I said I will talk about the Earth and her sisters. But then Ricky Royden said, but come on, he said, you're working on Mercury and Mars, they're boys. So I said, they have to be brothers. And then I thought about it, not really, they are the sons of Gaia. Look, it's too complicated. I will continue calling them sisters because planets look, for some strange reason, female to me. I don't know. The lecture is dedicated to the memory of 2 men who have illuminated our path in working on Mars and Mercury. One is Élie de Beaumont, who was really the creator of the geological theory of contraction. And he spelled out what sort of structures can form. And indeed, we found on Mercury structures similar to those that he had predicted. And the other one is Jovan Cvijic, who got his PhD in this city from Eduard Suess, and he's remembered as the great master of karst topography, although his contributions over spill karst, and they really start with the geology of Istanbul. He's one of the very earliest geologists who worked on Istanbul. The solar system, you see the planets here, including the very small ones, according to size, and the rocky planets, there's Mercury, Venus, Earth, and Mars. But some of the others probably also have rocky cores, of which we know essentially nothing. These are the inner of the rocky and terrestrial planets. I would like to just summarize their properties. Mercury has a magnetic field. It's about smaller than Earth. It has no magnetic field. The numbers that you see on these things here, refer them down on the list here. There is a density and there is a rho is density, rho u is non-compressed density. Then you have the G, which is the gravity on them, and we have the albedo and the surface temperatures. Although the surface temperatures change wildly. For example, on Mercury, if you're in the cold hemisphere, it's unbelievably cold. If you're in the hot hemisphere, it's unbelievably hot. So if you're in the middle, if you have a space station that moves by 2 kilometers per hour, you can stay in the habitable zone of Mercury. Now, these are roughly the internal structures of these planets. We don't know too much about them, because some of them we have not even visited. Venus and Earth, as you can see, are believed to be very similar. We know a lot about Mercury because of the MESSENGER mission. And what is amazing about Mercury is that it's missing a silica-rich crust. It's all mantle and not much of it. So the great question is what happened to it. Mars has a big mantle, and it is unlike the Earth. It does not now have a magnetic field, so probably nothing is convecting as widely as the Earth's crust is convecting. The atmospheres of the inner and rocky planets. Mercury has essentially no atmosphere, it's too small. Venus has a very heavy atmosphere, dominated by carbon dioxide. Mars has an atmosphere also dominated by carbon dioxide, but very rare. So it's lost much of its atmosphere. The Earth has an atmosphere that enables us to live, and it does so because of photosynthesis since at least 2,800 million years ago. These are sort of the general characteristics. Now, when we look at the hypsometric curves, this is very interesting. The blue is the Earth. And as you know, Alfred Wegener, many years ago, in 1912, first pointed out that this double-peaked characteristic of the Earth's crust probably indicated 2 domains of density. And we have learned since that he was right. Now, when I was a student, people wanted to believe that Mars had a single peak hypsometric curve, but Hartmann at the time had already started showing in the early 1970s, 1975 actually, middle 1970s. He started showing that Mars had a double-peaked crust, and now you can see here the most recent data show you that it has double peak because the northern hemisphere, as Kevin talked in his lecture, is dominated by a much denser crust. At least that's what we think. Venus is very funny. Look at that. This is almost an equipotential surface. It has a single peak. And it's almost at average elevation. It's zero elevation. This is the hypsometry of the northern hemisphere of Mercury. Please notice it resembles very much Venus, but not, we don't think, for the same reasons. This is so because the tectonic events that take place on Mercury seem to be very homogeneously distributed. And that is what I want to come to. This is Mercury. Okay, you can see that it does not have this almost equipotential fluid surface. It looks much harder, and yet it still has a single peak. I have now summarized textbook information for you, but we've learned some lessons from that. Mercury has the highest uncompressed density for all the planets of the solar system. Earth and Venus have similar densities. Mars consists of lighter material. Mercury is the smallest of the inner planets. Earth and Venus have similar sizes. Mars is half their size. Mercury has hardly any atmosphere. Venus and Mars have carbon dioxide dominate the atmospheres, although there's a huge difference in absolute amounts. Mars has lost much of it because it's smaller. Earth's atmosphere has 21% oxygen because it developed photosynthesis, but this 21% only is today. We know in the Carboniferous it went up to 35%, and then at the beginning of the Permian it plummeted down to 15%. So plant life and paleogeography determines how much oxygen the Earth will have. Earth and Mars have double peak hypsometric curves suggesting different densities of its crustal materials underlying different elevation groups. Venus's hypsometric curve is close to that of an equipotential surface, suggesting ready flowage of surface material dominated by a single composition. And this is in agreement with a very high surface temperature, more than 400 degrees centigrade. Mercury also has a single peak hypsometric curve, but it's flatter, suggesting a uniform tectonic activity affecting its surface. So what is that tectonic activity? First of all, let's very quickly go and look at the Earth. Earth has plate tectonics. It has these arcuate mountain belts in which there is much shortening. It has the extensional areas that create the oceans, and in some places the continents are now in the process of breaking up. Tectonic activity, as expressed by earthquakes, is largely confined to plate boundaries. Only in the continents they get scattered, but still in a very limited way. This is the way the Earth behaves is possible because it has much water overall. Its hydrosphere contains 386 million cubic kilometers of water. Now, after the discovery that OH ions may be hiding in crystal defects, it has been hypothesized that the Earth's mantle may have 1 to 8 times of the ocean volume sitting in there still. Total water we have in the Earth's composition may be 1 part per mil to 8 parts per mil. This tiny amount is more than enough to enable hydrosmelting to take place, which makes continents. Enables convection to take place in Earth's mantle, it moves plates. Imagine that a 50 pp part million of water in an ultramafic rock is enough to reduce its strength by 10 orders of magnitude. Tiny amount of water. And this is the result. There's a famous plate tectonic model. Everybody knows that. But if you move to Mercury, it's a completely different world. Everything you see here in white is a structure formed by shortening. It's either a thrust fault or it's a fold. They're mostly thrust faults. The folds are confined to the northern basaltic plains. The surface composition of red areas, which are also topographically high areas, is komatitic. They're ultramafic. The lower areas, have basalts in them, and they have formed. They're younger than the Komatiitic areas. Okay, the southern hemisphere is not so well known, but because of the Messenger mission, we know a lot about the northern part. And I don't know whether any of you have seen it. In April something issue of Nature, a paper by Paul Byrne and Christian Klimczek, myself, and Jean Solomon, etc., has appeared, essentially mapping the surface features of Mercury. It resembles the moon, but the difference is it has this huge fluid core, a little thin mantle, and essentially no crust. What we did was, Paul Byrne and Christine Klimczak, they were working as postdocs. And I asked them what they were doing. They said, well, one of them was working in the Caloris Basin. I said, why? He said, well, it's the largest impact basin on Mercury. I said, I repeat my question, why? I said, we know, if there is only one process we really know well that's impacting on the solar system. I said, Mercury has infinitely more interesting features. Why aren't you guys working on those? Before this paper, Mercury had been mapped tectonically. They had found 16 wrinkle ridges. If anybody knows what a wrinkle ridge, please tell me. This map contains thrusts and folds. Let's exclude the folds now. 5,600 plus thrust folds. The geologists could give the geophysicists only 600-meter radial shortening, where the geophysics demanded 10 kilometers. Now we're telling geophysicists that we probably have more shortening than 10 kilometers. These funny lines you see here, these are the lines along which we counted the structures. And these are some examples. I mean, look at that crater. Okay? There's a thrust fault. It goes right through it. And look at that. It's a Rocky Mountain type uplift. It seems as if it's bounded by thrust faults on both sides. Some of these structures pass into fold structures. Okay, here it is. And again, there's a fold belt. And look at the length of it. They're really amazing structures. And we can recognize syntaxes along them. You can recognize linkages. I'm showing these figures because these terms were invented in this city by Eduard Suess. We can apply his terminology to Mercury. Look at these. These are the low areas. And please notice that the highlands are overthrusting the low areas because of the higher potential. This is what Suess had called the Überschiebung der Tiefen. And some people have even got big awards for having rediscovered that. Okay, look at this. Again, high areas are delimited against the low areas in this. But I want to show you one very significant thing. This is a beautiful virgation. We call them germanotype because there are two types of folding. If you have a penetrative folding affecting the entire orogen, Stille had called it alpinotype. And these sorts of folds we have in the low areas. The high areas, you have these big basement thrusts. And he called them the germanotype, and you can make that distinction here. This is the Rocky Mountain virgation recognized by Eduard Suess in 1909. Please look at that. Sorry, this is 1885. And look at this. You see a very similar structure on Mercury. This is the Rocky Mountains drawn by William Holmes. These sort of structures are what we see on Mercury. Pitfalls are abundant. You have to be careful whether a crater predates the crater or it postdates. Or the crater predating fold and thrust belt here, fold and thrust belt postdating the crater. You can recognize these things only by looking very carefully at how the folds and thrusts are distributed around the crater rim. Okay. If the crater predates it, they nicely go around, but for example here, you can see the folds are becoming straighter and straighter as you go away from the crater, so the impact has pushed them to the side. Okay. We have used a very simple fall landfall thrust belt type calculation to get the shortening amounts on Mercury. The great advantage on Mercury is because you have no erosion. So you can just look at the elevations here, the wavelengths, and you can get the amount of shortening. When you do the entire mapping, you realize you get a history, and in that history, you recognize that the first event was these basaltic eruptions after the consolidation of the Komatiitic Highlands. And this is probably when contraction first started. When it first started, it burst the crust. The basaltic eruptions happened, and as the planet continued cooling, the level of no strain started sinking, and you start getting shortening on top. And this is, we believe, is the picture that we see today on Mercury. These are the alpino-type folds, if you like. These are the Germano-type folds. Does Mercury simply behave like Dana's shrinking apple? Well, you saw the picture. It does. And it takes a believer's eye to recognize consolidated areas, areas still weak, shortening, things like orogenic belts. We're not convinced of that yet. Still working on it. As data accumulate, things will be better. Let's go to Mars. Here's our next object of interest, that is Valles Marineris. Now in Valles Marineris, I would like you to notice that Valles Marineris is a huge negative structure. Its sides don't match. And certainly some people would like to see an offset here, a strike-slip fault. It's nonsense. There is no such thing. And it has little brothers and sisters. They are all closed depressions. And the Serbo-Croatian speakers will immediately recognize them as poljes. Well, this is the surface of Mars, topography of Mars. Again, notice this pronounced hemispheric asymmetry. This is thought to be the result of an impact. I'm not convinced of that, simply because along the margin, you do not see the sort of structures you'd expect from such a major impact. But I really haven't looked at it. This is the Tharsis Dome. There is Valles Marineris. That's where we want to go now. First of all, these pictures show that there is water on Mars. Something fluid, behaves like water. Okay, you look at the summer and winter pictures, obviously, something is flowing at the surface of the summer. Okay, these are called recurring slope lineae that are narrow, 0.5 to 5 meters. Repeat images show them to appear and incrementally grow during warm seasons. They extend downslope. These recurring slope lineae appear and lengthen in the late southern spring and summer from 48 degrees south to 32 degrees south, latitudes favoring equator-facing slopes, which are at times and places where you have peak temperatures from minus 23 degrees centigrade to 27 degrees centigrade, which is fine. Then you find gullies, and these gullies indicate that probably some of the water comes along layers. It doesn't flow on the surface. It flows along layers. And then it oozes out and creates these gullies. We know that Mars used to have a large ocean. This is Jelal Mitrovica has mapped the terraces that we see in the along the northern hemisphere, and he has shown that if you do the calculation, you can show that the differences of elevation is because of isostasy. Okay, two conclusions are inevitable. There is water locked up in Martian crust, and if it episodically melts, other liquid candidates would be carbon dioxide. They have been proposed but are unlikely. Periodic and near-surface melts are clearly seasonal. being caused by sun's energy. They're exodynamic. Non-periodic melts from deeper water reservoirs are not. They have to be endodynamic. The only source that can melt deeper water reservoirs on Mars is igneous action. Its presence of methane, corroborates that. It's speculated that volcanicity on Mars may have been active as recently as the very latest Amazonian, that would be Cainozoic, extending into the Pleistocene. Okay, and Hartmann as well pointed out the most recent activity in Olympus Mons, Mars's largest volcano, occurred at the summit around 150 million years ago, with minor flows in some areas as recently as 2 million years ago. I mean, this is Pleistocene. Okay, this is a suspiciously straight object. But this is a slide by Kevin Burke, drawn when I was still almost a child. And Kevin said, he went to this meeting, he talked about also the chart basin. He said the audience rose as a body to tell him he was full of shit. And he was right. Here, that's the East African Rift Valleys, and notice they really don't look like Valles Marineris. Valles Marineris is huge, but the Valles Marineris looks like these closed depressions. They're called poljes. This is Johan Sweech. He named these things, the big karst features, tectonically controlled karst features, in the Dinaric Alps. He called them poljes. Okay, this is a fault-controlled poljes. He also suggested they could be synclinal poljes. We don't see them on Mars, but we are sort of suspicious about these. And this is Armin Kohl-Lobeck in his great geomorphology book. He took Sweet's figures, drew them more nicely, and please impress this into your head right now, into your brains, because we're going to look around Valles Marineris. You'll see very similar features. It is unlikely that Mars have extensive carbonate platforms on its highlands. If so, whence is the great resemblance between the karstic poljes and the Martian chasma? A possibility is thermal karst caused by dike injection. Weyrich et al. Invoked dike injection to form pit crater chains. They are, as in Afar, I mean, they're very clear, but did not associate it with a thermal karst. Okay, so how are you going to do it? Well, we propose that if you have a layer, a rock layer, but composed of H2O, the lithosphere structure would have either pure water or water-saturated layers. And then if you have a dike injection, you would create these closed depressions. Well, does that make sense? We performed analog experiments to see whether thermal karst produces structures analogous to poljes. This is our experimental setup, water ice here, bentonite or flour on top, and here's a resistance coil. You heat that to simulate the dike. And there's the experiment table. There is the coil that goes through here. Okay? And the granular material, this is a cross-section, granular material on top. That's a resistance coil. And that is the water layer, or ice. Bentonite experiment, these are the parameters. I'm not going to bore you with the parameters, but I'll leave it on a few seconds for you to sort of assimilate what sort of scales we're talking about. Okay, we start heating the coil. That means the dike injection started. This is the initial subsidence. We call them down-drop faults. They're neither normal nor thrust because they go straight down. Look, new set of down-drop faults forming. Progressing subsidence. This is the growing thermokarstic polje atop the dike. New set of down-drop faults forming. If the dike remains hot in our experiment 10 minutes, the polje begins growing sideways. But look at within it, you get different fields of subsidence, and they all have the same shape. Narrow, long, rounded ends. This is the digital topography of the thermokarstic polje formed during the experiment. This is the true scale. This is the, if you do it 5 times exaggeration, this is what our experimental polya looks like. Then we replaced bentonite with flour, and again, these are the parameters. I'm not going to bore you with parameters. Okay, initial subsidence of the thermocaustic polya. Progressing subsidence after 3 minutes of resistance heating. Progress of the subsidence of the polya 5 minutes after the heating. Mind you, the polya starts subsiding in one place, although the resistance is heated up uniformly at the same time. This is after 5 minutes. Shape of the thermocaustic polya 8 minutes after the onset of resistance heating. Look at that. Look at the ends, please. Look at the sides, how it sort of tries to grow. That's the end. And these are the polya within polya structures. These are beautiful steps that form. This is the topography of the flower experiment at true scale. Please notice these steps. This is topography of the same after 5 times exaggeration. You can see them more clearly. This is not from our experiment. This is from Mars. It's the similarity is unbelievable. This is Valles Marineris, same color as our topographic scanning of our experimental polya. And please notice here, look at the side valleys. Look at these. Completely closed. You cannot make them tectonic. And look at these crater chains. If they are indeed formed atop dikes, this is what you would get. And if you go to the end of Valles Marineris, what do you see? You see huge flooding. That's what we saw in our experiments. If you leave the experiment long enough, the whole bottom collapses, water oozes in and floods the polya. Again, this is Professor Sakunch. His finger is pointing out to the end of the polya. Look at these. Look at that. Look at here. These are the various stages at which probably the polya progressed, and there's the big flood. This is the scablands of Mars, the giant scablands of Mars. So how reasonable is the giant dike hypothesis? In other words, do we have analogous cases elsewhere? Great Dike, it's huge. This is the Grand Canyon. Grand Canyon is that big. The best analog we have is the Mackenzie Dike Swarm. This is almost as long as Valles Marineris. It has satellite dikes, and therefore it could have created this. And look at the distribution of radial patterns around Tharsis. Okay, gravity anomaly, crustal thickness. You know, you can look, the crust is completely thin in here. Okay. And this is a crude attempt at telling you what the dikes may have looked like under Mars. These are 3 planets. They have very similar material, completely different histories, but same geological methods that we use on this planet as field geologists are applicable. NASA spends billions for engineering projects. The geological analysis of these things, I have found it best amateurish. We need more geologists with terrestrial experience with this.
Thank you very much, Taylor, for this impressive talk. There's a little time for questions.
You haven't swallowed anything
yes,
I said.
Please.
It's quite an interesting talk, thank you very much for that. I was wondering, you have shown us hypsometric curves of terrestrial planets. In Mercury, we could easily see that it's a Gaussian process that have created such a distribution, a single peak, and it fits with the shrinking or Elie de Beaumont's theory very well.
Well, but it fits not so much with that, but more with
analogous
homogeneous distribution of the deformation.
Okay. But I would like to jump up to Mars. You have two modes of distribution there. That indicates there are at least two domains of different crustal types. Okay. Now, you have shown that valles marineris have formed by perhaps dike injection that fits your models quite nicely. But do you think it happened after the stopping of plate tectonics, which probably...
Well, valles marineris probably formed about more than 3 billion years ago. It's a very old feature.
Because this double peak distribution usually can be attributed to the existence of plate tectonics that was originally Wegener's
I have tried that. It didn't work because you don't see the structures.
Okay.
Maria Zuber and company have tried to explain it with impacts. The problem with that is an impact of that size would have created a circumcrater mountain belt. However eroded it may be, you would see evidence of that. I have seen none. Kevin, do you know of any evidence for that? Do you know of any evidence that the initial big impact forming the northern hemisphere of Mars having created any marginal chains?
Not to my understanding, but I'm not a specialist on that.
Well, I mean, you know more than many specialists, so that's why I would like to ask you.
Okay, thank you.
Okay. Thank you very much. I think we're stopping at this point.
I am amazed that my good friend here, not asking me quickly, there is the master of Eustacy, and I just said on Mars there were oceans. And Bilal is sitting quietly. I showed some shorelines.
Okay.
Which were proposed by his nemesis, but he's not saying whether Eustacy worked on Mars.
That's okay. Okay. Thank you very much, Tilal. And we're moving on to the next speaker. I'm proud that Heather Wiles is available to give an invited lecture on the topic of the face of the Earth. Heather, the stage is yours.
Thank you very much. And now for something completely different. I want to pick on the heritage that Eduard Suess left us in a very different sense, picking on some of the work that geomorphologists do, and specifically looking at how we might better link life and landscape. So there are three main points that I want to cover in this talk. First of all, I want to say a little bit about what geomorphologists do and the fact that we study landscape dynamics. The main part of the talk, I want to discuss some of the major growths that there have been since 1914, when Suess died, in the technology available to geomorphologists, allowing us to answer even more important questions. And so I want to link that to thinking about how we're becoming increasingly interdisciplinary as geomorphologists and using our understanding to try and address some really big questions. So Eduard Suess, as you know, died in 1914, and interestingly, he was born in London, and the Geological Society of London have erected a very nice plaque to him as a memorial. But rather more importantly for us are Eduard Suess's key ideas about the face of the Earth, in terms of what geomorphologists might see as the face of the Earth. So firstly, as you know, he hypothesised the existence of Gondwanaland and the Tethys Sea, things that we now know have had a huge impact on shaping the current landscape on Earth. But very importantly as well, Suess introduced the concept of the biosphere, and this little quote comes from The Face of the Earth, Volume 4, saying that he came up with the idea of a biosphere, which assigns to life a place above the lithosphere. And one key point here is that Suess was drawing on many contemporary ideas, thinking about the relationship between life and landscape. But as you can see in the way that he framed it, the biosphere was above the lithosphere. And what I want to illustrate quite a bit in this talk is how we now know the two are much more clearly intertwined. And this knowledge about the intertwining of life and landscape really predates Suess and comes from some very important workers that he himself quoted in the preface to The Face of the Earth. So firstly, we should go back to Charles Lyell, seen here as a young man in his early 40s. I'm really fed up normally when you see all these portraits of people in the past in their ancient stage. And I think it's very important for us to remember that they were once young. And Charles Lyell, as you can see, wrote a lot in his famous book, The Principles of Geology, on how life and landscape were intertwined. In this particular example, he's talking about the powers of the organic creation in modifying the form and structure of the Earth's crust. And he points to the importance of corals and also the plants which generate peat on land. So a geologist in the 19th century acknowledging the way in which life and landscape are intertwined. And perhaps even more interestingly, Charles Darwin, again seen here as a young man, not only recognised this importance, but did some very early pioneering quantification of it. And the quote comes from, I think, his masterpiece, The Formation of Vegetable Mould Through the Action of Worms, with observations on their habits. How about that for a sexy title for a book? But this book was tremendously important. In his back garden, he measured the amount of material that worms were passing through their bodies in terms, therefore, of bioturbation, in terms of the very Earth's surface processes which geomorphologists study. Now, against a backdrop of these ideas, over the last 100 years, there have been huge changes in the way that the geomorphologists see themselves and see the major focus of their research. So one commonly used analogy that geomorphologists over the ages have used is that of the face of the Earth being like a palimpsest, where a palimpsest, there's an example here, the Archimedes palimpsest, is a parchment where there's been an initial writing, in this case going from top to bottom, some ancient writing of Archimedes. And then, because parchment was expensive, they reused it by trying to rub that out and rewrite over it. In this case, 13th century monks writing horizontally across it. And many geomorphologists and others have interpreted our landscape around us as being very much like a palimpsest. Layers partially raised, layers created by former Earth's surface processes, then partially erased by newer ones. And we'll come back to that analogy later on. Another analogy, which I think is quite an interesting one, is to see the face of the Earth, the terrestrial landscape, more as a ruin. And this comes very much from the fashion for looking at ruins in the landscape. This is an example from 1806, an engraving of one of the great ruined abbeys of Yorkshire in England. The notion here that erosion over time is creating different landscapes, and they are in turn becoming more and more ruined, and in this case through the interrelationship of organic action and physical and chemical processes. But clearly the more modern view of geomorphology is geomorphology as part of the Earth system. And this is the face of the Earth seen as an interacting system. And these sorts of diagrams are often shown where we have air and water at the top and land and life at the bottom. And land we might see as the major area of research for geomorphologists and geologists. We'll let them share a little bit. And life, of course, is the field of research of ecologists and biologists. And what we understand now by the Earth system is that these interacting parts of the system are all hugely important and cannot be separated realistically. Now, this is where geomorphologists are now tremendously important. Instead of just thinking about a palimpsest or a ruin, we're now thinking much more big in terms of trying to address some really big Earth system questions. And some of the key questions that geomorphologists are trying to focus on now are summarised firstly by how the landscape interacts with other parts of the Earth system over all temporal and spatial scales, past, present and future. That's kind of the big question geomorphologists focus on. And I put here two questions which are also very important in terms of our interrelationship with the Earth system. So how have humans influenced landscape dynamics, especially over the Anthropocene? And secondly, how resilient is the landscape to extreme events? How resilient is this human influence landscape to things such as the winter storms that we've suffered recently in UK and other parts of Northern Europe? And these questions are things which geomorphologists now contribute to. And my argument is that we contribute to them even better by being interdisciplinary and thinking about life and landscape as much as possible together. So what I want to do now is show how things have changed in our attempts to do this since 1914. 100 years of progress, and I want to reduce it to 5 technological innovations. And I want to start doing this by looking at a quote from Suess's book, the start of Volume 3, confusingly called Part 4, where he introduces this by looking back to how the book started. And he said, "We began our study of the face of the Earth by imagining an observer to approach our planet from outer space and pushing aside the clouds of the atmosphere to contemplate the surface of the globe rotating beneath him. We then supposed that this observer, as he had previously pushed aside the clouds, was now able to remove the sea so that he could gaze directly on the bare rocky crust and on the great abysses of the ocean." Now this to Suess was only a dream, but of course now to us this is reality. We can now visualise and probe the surface of the Earth, the face of the Earth, in a whole series of ways that Suess simply couldn't imagine. So the first technological innovation I want to talk about is our ability to view the face of the Earth from above. So moving from air photography through to remote sensing, down to LiDAR, and to our new best friend as a geomorphologist, UAVs, which now provide a fantastic opportunity not only to observe the horizontal face, but to look at things like cliffs, which are very hard to observe from these other methods. And the fact, of course, that we not only view the landscape now using these techniques, but we can quantify the topography and many other aspects of the surface of the Earth using these techniques. Air photography clearly started very early, but some of the most important early air photos date from around the time of the First World War for very obvious reasons. For example, this air photo montage of coastal dunes taken in 1916 gives a very good example of how geomorphologists use this kind of repeat imagery to look at change on the face of the Earth, and change in terms of sediment dynamics and also plant community responses. If we took the same air photo montage now in 2014, we would find that most of this was built upon. The landscape has changed hugely. Geomorphologists now, of course, make use of other types of evidence as well as that of air photos. Google Earth and other virtual globes now permit free, easy access to data sets which can then be quantified in order to provide good categorization and understanding of the morphology of different parts of the face of the Earth. I'm terribly sorry, this is proud mother alert. This is my younger daughter's first scientific paper coming out of her undergraduate dissertation. Perhaps a good example of how these techniques are really easy to use and are being grabbed and taken forward by the geomorphologists of the future. My second technological innovation that I want to talk about is geophysical methods which allow us now to get under the skin of the face of the Earth. Moving through this image, we can see magnetic surveys, GPR, and electrical resistivity tomography, all now heavily used by geomorphologists. The first German patent for the use of GPR to detect buried objects was granted in 1910. And since then, there's been a rapid uptake in the use of these techniques to answer 2 sets of geomorphological questions. Firstly, to tell us more about the archives in the surface of the Earth, the nature of the materials within the shallow subsurface and the history that they reveal. And secondly, to tell us more about how processes operate within this shallow subsurface and have huge impacts on the surface. And the example I want to give comes from a poster, which I hope you'll all go and look at, by Austrian colleagues, working on granite Tafoni at Tafraut in the Anti-Atlas in Morocco, and using things such as ERT, electrical resistivity surveys, to understand how these Tafoni, these weathering features, are being formed at the moment. And you see my colleague Oliver Sass there defying all known forms of risk assessment to carry out some field work around this ERT survey. My third technology in innovation, which has dramatically revolutionised geomorphology, of course, is the now very large suite of dating techniques available: radiocarbon, OSL, U-series, cosmogenic, and a whole suite of other techniques. And again, the start of these came in 1905 with Ernest Rutherford's great discoveries of radioactivity, and permitted these quantitative assessments of the history of various parts of the Earth's surface. And the time spans now that geomorphologists can understand are really very varied using these techniques. So, for example, here's Dave Thomas and Abby Stone on the right here from our department in Oxford, carrying out sampling for OSL dating of parts of the Namib Sand Sea. And in this paper and a suite of other papers, Abby has started to wrestle with how these dates can be used to interpret changes in the recent past over the Quaternary, and also the problems, the new questions that are posed by this kind of dating evidence. Questions that urge us to think about what we mean by dating a landform or a process. My fourth important technological innovation for geomorphologists in the last 100 years is a whole suite of relatively small, field-portable and fairly simple bits of equipment to tell us more about the physical and chemical makeup of parts of the surface of the Earth. So on the top left there we see a portable XRF, very useful for telling us about the composition of materials. In the middle we see one of my great friends and loves in life, the Schmidt hammer, originally devised in the early part of the 20th century as a concrete test hammer, now widely used to assess rock hardness and by implication the weathering status of rocks on the surface of the Earth. And finally, in the bottom right, hyperspectral imaging cameras, also used now to study historic documents like the palimpsest I showed you earlier, but also in turn very useful for providing ground-based detailed assessment of the surface materials on the face of the Earth. And these are not necessarily hugely sexy bits of kit, although the hyperspectral imaging camera is, but they're very useful in providing additional information for geomorphologists. So to give you an example, here's some work we've been doing in the Golden Gate Highlands in South Africa, looking at variations in rock hardness as a proxy for the degree of weathering, and using a range of equipment, not only the Schmidt hammer, but smaller, different rebound hammers devised originally for different purposes. And here we have my husband. It's always important to have a picture of your husband on his knees in every lecture, failing to use one of the rebound hammers correctly, but helping me to determine how we can use these in association to tell us more than one single method about the materials making up the surface of the Earth. And this is just to show how different instruments correlate to variously good degrees and start to tell us different things about these materials. My final technology is the one that I'm most excited about, the innovation that is really grabbing the attention of geomorphologists and helping us to untangle life and landscape over many scales. The ability now to identify things using PCR and things like 454 pyrosequencing techniques to tell us about the DNA, the very identification of things growing on the surface of the Earth. And whilst this might sound more to do with biology, I want to give you two examples of how these techniques are most important to geomorphologists. Firstly, I want to go to look at some sandstone outcrops. These are, for example, in southern Poland. They are covered, as are many surfaces on the Earth's land by a whole range of microorganisms. And these microorganisms are very important in weathering, crust formation, and a whole load of other biogeochemical processes. But we've been largely unable to identify them until recent years with the advent of this culture-independent methods, which are now fairly cheap and very rapid to identify what's growing. And so, for example, what's growing on rocky outcrops, we can also look at what's growing on walls. And here's an example from Belfast. The walls of many parts of the northwest of Britain are now going green, having gone black in the past. And our work has been trying to look at what is causing the greening and identifying the range of organisms found. And the point I just want to make from these numbers is using pyrosequencing and other techniques, which, as I say, are now cheaply and easily available, we're finding a vast diversity of life in these relatively hostile environments, which we didn't know anything about. And other useful biological techniques now help us find out what these things are doing and how important they are to the geomorphology we see around us. But my final example comes from a really nice paper by Paul Baker and colleagues in Press in Earth Sciences Review, where they propose the term geogenomics to show how looking over longer time spans, understanding the phylogenetic structure of organisms in different areas, can help untangle some interesting geomorphological and geosciences questions. So if, for example, you see a split in a lineage of a phylogenetic tree on the left at a certain time, and you can correlate that perhaps with geological or climatic changes, that helps you to date and understand the processes around us. So Suess's biosphere can really help inform us in our work as geomorphologists. So just to finish off then, I believe that today's geomorphology has been very much shaped by these 5 technological advances, which we link together with each other and with other parts of the Earth system through increasingly sophisticated modelling. We now really do have the potential to have a 5D view of the surface of the Earth. And our increasing interdisciplinary work is now allowing us to answer some really big questions and show that geomorphologists are not just useful in terms of deciphering a palimpsest, but also thinking about what that means for life and landscape on Earth. And I just want to finish by this quote from Suess, which I think is very relevant even today. This is from the end of the book. In face of these open questions, let us rejoice in the sunshine, the starry firmament, and all the manifold diversity of the face of our Earth, which has been produced by these very processes, recognising at the same time to how great a degree life is controlled by the nature of the planet and its fortunes. I would equally argue now that we know the planet and its fortunes are controlled by life. Thank you very much.
Thank you very much for this stimulating talk. Questions or comments, please? You ready? Let me ask you a first question to start the process. There were 5 technological advances. If you were asked to name one conceptual advancement in the period, what would you name as the most important conceptual advancement in geomorphology in this period?
I think the notion of the complexity of responses of geomorphic systems, and that clearly conceptual advances tied up with conceptual advances in all parts of the geosciences. The recognition that there are huge numbers of non-linearities within the system. This is a conceptual advance that geomorphologists have wrestled with ever since the 1960s, but only been able to deal with perhaps better mathematically in very recent years. But to me, that's the most important.
Okay. Sure. Pardon me?
Do we have time for another question?
Sure, yeah. Go ahead.
I was curious whether you've looked at other planetary surfaces now, because we can see them in much greater details, and we know what factors are missing there, and how that affects the sorts of landforms, landscapes that we see from these planets. Have you sort of tried to make a comparative list? and try to deduce genetic answers from that?
That's a very good question. There is a huge interest in whether there's a key signature of life on planetary surfaces, and there's been some very interesting work on that. I, in collaboration with Mary Burke, have done some work on looking at rock breakdown on Mars and trying to see whether we see any specifically. We see things that frankly look very like the Atacama and certainly places in southern Libya. So they look pretty similar at this stage.
I mean, it looks like the Sahara. I was in southern Libya, I agree. But nothing really specific to life. Even in the Sahara, I can see anything specific to life.
Well, there's a big debate over it, really. I think the problem is because of this palimpsest and because of the complexity, untangling things over, especially on Mars, the very long time spans, I think can be very hard.
Okay, thank you. Are there any other questions or comments? Okay. Yes, there's one.
A similar question. Would it be also possible to reverse engineer, for example, the conditions that were hypothesized in the UV Miller experiment, where they first show how amino acids could have been formed, and is there anything corresponding to that where we can go and look for the first elements of life at all, maybe RNAs or amino acids or something like that?
Very interesting. I don't know is the answer to that, but I'm sure there would be the possibility to do that.
Okay, thank you very much. The last speaker of our session is Anne Cazenave. Please come forward, and she will relate the face of the Earth to sea level changes. Anne.
Okay. So, thank you very much. When President Bloschel invited me to give a presentation in this session, as well, I was not sure which topic I should cover given my own area of expertise, which is space geodesy. So after some thinking, I decided to give a brief overview of what we have learned during the past 50 years with satellites about the shape of the Earth, including the sea surface, and addressing both permanent or non-variable shape of the Earth and the time variable shape of the Earth. So, as you have seen in the previous two presentations, we have heard mostly about the face of the continents, and in my presentation, at least partly, I will talk about the face of the ocean. So, okay, let me start from very far away in the past. This figure illustrates that during several millennia, our understanding of the shape of the Earth did not evolve very much until the late 50s, that is the beginning of the space era. We only knew that the Earth was a kind of spheroid flattened at the pole. But the situation totally changed with the beginning of the space area. Space geodesists, by studying the deformation of satellite orbit, discovered that the Earth has a very complex shape. It is a bumpy body, as we will see. And this complex shape of the Earth can be visualized by what we call the geoid, which is an equipotential surface of the Earth's gravity field that coincide with the mean sea level. That is, if the Earth were totally covered by water, the geoid would represent the shape of the Earth. And this geoid variation, by the way, reflect regional variation in the gravity. So over the last 50 years, space geodesists have provided a series of different generations of gravity field or geoid models. And these are shown here, the evolution through time, and mostly with increased resolution. Until recently, until 2009, when the European Space Agency launched the GOES satellite, a satellite that carried an instrument called a gradiometer that directly measures the component of gravity, of the gravity field, or the geoid. And in just a few months, GOES, not GOES, sorry, I will talk of GOES in a moment. GOES provided a new model of the gravity field or of the geoid with unprecedented accuracy. So what you see, you all know that the Earth is not round. It is a bumpy body, as I said before, with geoid highs and low of a few 100 meters amplitude. So it is now well known that these geoid anomalies, geoid highs, like, oops, oh, sorry, the classical problem with, okay, I have to go back, okay. Okay, so you can see this geoid high here, geoid low here. So it is now well known that this long wavelength geoid anomaly reflects as the surface expression of large-scale mantle convection. And during the past 30 years, geophysicists have studied jointly geoid data, long wavelength geoid data, with thermal data of the mantle, of the Earth's mantle, as provided by seismic tomography to produce or provide the viscosity structure of the Earth's mantle. Okay, just to show the very high correlation between the long wavelength geoid anomaly and the thermal structure of the lower mantle. Okay, so at shorter wavelengths, the geoid, the Earth surface is also not flat, or the sea surface is also not flat. But that was discovered much later using a different tool. That is, the tool is altimeter satellites. So satellite altimetry is a technique that provide mapping of sea surface height with respect to a fixed reference with very dense coverage, as illustrated on this figure, which shows the coverage of the Earth's surface using satellite altimetry in just a few days. The Earth's surface, the sea surface, in fact, has two components. One permanent component or quasi-permanent component that coincide with the geoid and reflect the geographical gravity field variation, typical amplitude of a few meters, and a time variable component that reflects ocean dynamics, that is ocean currents, tides, sea level rise, as we will see in a moment, of much lower amplitude, typically a few centimeters or a few decimeters. So with altimetric satellites, the first results that were obtained were on the permanent component or the mean sea surface, which is shown, an example is shown on this figure. So you can see here the highs and lows of the mean sea surface or marine geoid, and it has been instantaneously recognized that the mean sea surface is a kind of gravitational images of the seafloor topography. So from this data set, a number of geophysicists have inverted this data to provide global maps of the seafloor topography with very high resolution, a few kilometer resolution everywhere over the oceanic domain, with a lot of application in particular in marine geophysics, marine geodesy, marine geophysics. So at the beginning of the 90s, the accuracy of altimetric system improved greatly. Since then, it is possible to measure the sea surface height with an accuracy of 1 to 2 centimeters. So this means it is possible now to study ocean dynamics, that is, as we will see, ocean currents, sea level rise, etc. because these signals, as I said before, are much smaller than the permanent highs and lows of the mean sea surface. So one of the main applications of satellite altimetry was the determination of the ocean circulation. The large-scale ocean circulation give rise to what the oceanographer calls dynamic topography above the mean sea surface. This dynamic topography is different from the dynamic topography due to mantle convection, but the name is the same. Because of state of equilibrium called geostrophic equilibrium or geostrophy, the velocity of ocean currents is proportional to the slope of the sea surface. So by mapping the sea surface by altimeter satellite, it is possible to determine ocean currents or the ocean circulation. And you have an example here showing the Gulf Stream regions, and in particular the meanders of the Gulf Stream as determined by satellite altimetry. It is very important to know the ocean circulation for many applications, including navigation, but one of the reasons for studying the circulation is to better understand the role of the ocean in the climate system. In effect, the ocean compared to land surfaces or the atmosphere has a very big thermal inertia. It is the main reservoir of heat in the climate system, and it transports and redistributes heat in the climate system over time scale much longer than the atmosphere. And for that reason, it is called the long-term memory of the climate system. So knowing how the ocean transport and redistribute heat laterally and from the surface to the deep ocean is really an important question. Another application of satellite altimetry is the measurement of sea level rise caused by anthropogenic global warming. So this application is really the most demanding of the satellite altimetry, in satellite altimetry research, because the signal to measure is very small, just a few millimeters per year, as we will see in a moment. So here, this is an animation that shows the evolution of the global mean sea level as measured by altimeter satellite since the beginning of the 90s, exactly 1993. And you can see a clear positive evolution. It is a global mean sea level rise. And here, on this figure, just a plot showing this global mean sea level curve. Measured by altimeter satellites in 1993. If we compute the rate of rise, the mean rate of rise over this time span, we find a rate of about 3 millimeters per year, which seems to be a very small number, but in terms of global means, this corresponds to an elevation, a global elevation of more than 6 centimeters. So using other data, in particular space data, we are able, and in situ data, not only space data, we are able to quantify the various contributions to this global mean sea level rise. And we know that for the last 2 decades, ocean warming, that is thermal expansion of seawaters, explain about a little less than 40% of the rate of sea level rise. And land ice melt, that is melting of mountain glaciers and ice sheets, Greenland and Antarctica, explain about 50% of the rate of sea level rise. And we have a small contribution from change in land water storage. So for these two contributions, these two components can be measured from space using this corresponds to mass redistribution as the Earth surface, and this provides change in the Earth's gravity field and in the geoid. And this is now measured routinely by the Gray Space Mission, launched in 2002. GRACE provide measurement of the temporal variation of the Earth's gravity field that are interpreted in terms of mass variation or mass redistribution at the Earth's surface. So here you have an animation of the change in mass of the Greenland ice sheet over the last decade. And the blue, violet, and black color correspond to regions where this ice sheet has been losing mass during the last decade. And we can show a similar animation for Antarctica, in particular West Antarctica. These two regions have been losing mass at an accelerated rate since a few years. So this is a change in mass, but this is a change in the gravity field or geoid, so of the face of the Earth. Similarly, using GRACE, we can also map the change in land water storage. You have here again an animation showing as a function of time the region of the Earth, in particular the large river basins, where depending on which at which time you have either less water or more water compared to a multi-year average. So this is a component to sea level rise, because when you have less water on land, you have more water over the ocean, and inversely. And here again, you have an illustration of the changing shape of the Earth's water component on land. So another example of the changing shape of the ocean is this one here. You can see the regional variability in the rate of sea level change over the last 2 decades, mapped by altimeter satellite. In effect, satellite altimetry has shown that the sea level rise is not uniform. In some regions, like for example here, the Western Pacific or South in Austral Ocean, in this region, the rate of sea level rise has been faster than the global mean by a factor of 3 to 4. So this is another example of the changing face of the ocean over the recent years. So we are able to explain why there is a non-uniform sea level rise, and the main cause of that observations, of that processes, is non-uniform thermal expansion. Here you have 2 maps, one showing the observed sea level trend patterns revealed by satellite telemetry over the last 2 decades. The global mean trend has been removed. And on the right-hand side, you have the non-uniform or special trend pattern in thermal expansion. And you can see that there is a very high correlation between these 2 maps. So the fact that the thermal expansion is not uniform is due to the fact that in some regions, and in particular in the Western tropical Pacific, the ocean have stored more heat during this period than elsewhere, and this has caused a faster sea level rise. But this process is not the only one causing regional variability in sea level. There is another process, which is large-scale water mass redistribution due to past and present-day land ice melt. This process, because the Earth is not rigid, it is viscous, the mantle is viscous and the crust is elastic, these deform ocean basins, and this causes changing mutual gravitational attraction between the ice bodies and the melted water. And this causes ultimately regional change in sea level. And these changes are very complex. This is illustrated on this figure. For the past, when we talk about past land ice melt, we refer to post-glacial rebound. That is the response of the solid Earth to last deglaciation over the last 10, 20 years. And this process has caused a very complex deformation of the rebound of the high latitude continental region and very complex deformation of ocean basins. Ongoing land ice melt from Greenland and Antarctica are also supposed to give rise to complex deformation of the continent and of ocean basins, as well as change in land water storage. These processes are, today they are not yet observed because the signal is still very, very small. Sorry. But they are computed theoretically, and they are supposed to give a very strong response in the coming decades with increasing ice mass loss from Antarctica, from Greenland and Antarctica. So just to illustrate the changing face of the sea surface due to present-day land ice melt, here you have a map showing the change in the sea surface or sea level due to Greenland melting and Antarctica melting. And this is based, as I said, on a theoretical calculation. And what you can see is that in the vicinity of the melting bodies, Greenland or Antarctica, you have, because of the deformation of the solid earth and ocean basins, you have sea level drop and sea level rise in the far field, that is here mainly in the tropics. And this process is supposed to give rise to an amplification of the rate of global mean sea level rise due to global warming by 20 to 30%. And in the coming decades, it will be an important contribution to the regional variability in sea level. So to conclude, as we can see, the changing face of the Earth is an expression of the multiple processes acting inside and at the surface of the planet on a broad range of spatial and temporal scales. And this is so because the Earth is a complex dynamical system. All components from the deep interior to the surface fluid envelopes respond in a very complex way to internal processes and to external, from the sun, from human activities, even from planetary gravitational attraction. So they respond to external forcing, and they interact mutually again in a very complex way. So to better understand the changing face of the Earth, at least on time scale from years to 2 decades, it is very important to observe all components from far, from space, using satellites, and definitely observing the Earth globally from space on a very long time scale. When I mean long, as a space geodesist, I mean decades, several decades, is a very important goal. So I think I stop here, and thanks for your attention. And I can answer some questions if you want.
Thank you very much. Yeah, I learned a lot in your talk. Any questions or comments? Yes, please.
How do you measure the differential uplift of subsidence of the sea surface, independent of the satellite altimetry?
Independently?
Independent of the satellite altimetry. You said satellite altimetry gives us that it's something else.
So there are several, we have other tools, for example, tide gauge. Along coastline, tide gauge gives directly the relative sea level with respect to land, to the coast. So for impact of sea level rise, this is a very important information. We can measure the vertical motion of the crust using geodetic techniques like GPS, for example, VLBI, and so on. GPS, of course, use satellites, but you have the station, receiving station on land. So
you measure land, and then you look at sea level change.
GPS provide vertical motion of the crust. So we can, by combining GPS, tide gauge, and altimetry, we can separate the various components.
Okay, thank you. I have a question. You were saying the sea level rise is spatially not uniform, and
Yes.
this is partly due to spatially non-uniform thermal expansion.
Yes, this is by far the main component, at least today,
Please
but
understand.
also in the coming decades.
But I wonder, why is the thermal expansion non-uniform?
It's because, okay, it's not the ultimate answer, but it's because you have more heat stored in some region. Like, for example, for the last 2 decades, what we observe is that thermal expansion is higher in the western tropical Pacific. This means that there is more heat stored in that region.
Sure.
Ultimately, it is linked to the way the ocean circulation transport heat by ocean.
Changes in the ocean circulation.
Yes, yes,
Okay.
mostly.
Yeah. Okay. Thank you. And yeah, please.
Yeah, I think your animations were really wonderful. I really enjoyed that part, the talk. My question was about geoid. Does the geoid anomalies, do they move around? And if they do, at what time scale do they move around?
Which animation are you referring to?
Well, I'm not talking about any animation particular.
Okay, with Grace. I don't know if it is the right answer to your question, but with the Grace satellite, which is a really revolutionary mission, we can measure all mass redistribution. What we measure is change in the gravity field, so in the geoid and face of the Earth. But so this can be interpreted in terms of mass redistribution at the surface of the Earth. Over the ice sheet, we directly have the change in mass of the ice sheet. So over land, over river basin, we measure a change in water. Change in water storage, either due to change in volume of lakes, for example, or water in aquifers, change in water in aquifers due to water pumping for irrigation, for example. We can measure everything with Grace, and the big problem is the continuation of this mission, because as you said, space is very expensive, and it is maybe geologists can go on the field, but to study this kind of global phenomena, we need satellite definitely. And because it is very expensive, it is very complicated to have the long-term coverage of this phenomena.
Well, I mean, if you've seen how geologists waste that information, my God, I'm terrified.
Okay.
I don't know if I answered your question, but we can talk more about that. Okay.
Any other
Oops.
questions or comments? Thank you. If not, I would like to thank you again, Anne. And thank you again, all the speakers, and indeed the audience, for being present at the union session. Thank you very much.